Greetings. So this is fun. We're now going to shift. We've had 3 weeks of thinking about dynamics, and of course that's great because biological systems. I shouldn't say biological systems. That's too vanilla. Living organisms. Life is dynamic, and so it makes sense that we talked about dynamics for all this time. But now what we're going to do is we're going to go down a different path. And, in some ways I think of this in a way like the view of the world through the fly's eye. And what I mean by that is the fly's eye it's got this beautiful hexagonal structure. And I don't know what it's like to be a fly, but I kind of imagine what it's like to look at something through the fly's eye. And so these different, I think maybe they're called ommatidia, these different ommatidia, maybe each one of them sees the world a little bit differently. And so the dynamical picture that we had before was a very good way for us to be thinking about the living world. But now what we're going to do is we're going to adopt my latest passion for thinking about biology. And that's something that with my book co-authors, Yannick Kondev, Julie Theriault, Hernan Garcia, Christina Hishan, that has become a big theme of the third edition of our book, Physical Biology of the Cell. Not that I need to be talking about the fact that I work on books or something. I know that sounds pretentious, but it's really a reflection of the fact that in some sense it's too much to say it this way, but I'm going to say it. It's like it's all I think about. So it comes as no surprise that it's always on my mind. How should we think about biology and what are the principles? I love the fact that people like Bill Bialik, he wrote a book on physical biology or biophysics whose ambition is to find the principles. That's awesome. And if we don't try, we're not going to find them. So anyway, this theme, the theme of the coming couple of weeks, is one I'm really excited about. In fact, I'm excited about everything to the finish line of the course because it's the parts of the subject that have to do with lifeiness. Like when I talk about gene expression, I can cast that in a sort of, I can fake it out and cast it in the language of statistical mechanics. So it almost looks like a ligand receptor binding problem or something like that, at least in some cases. But here what I want to do is I want to tackle the big issues where it's just clear the periodic table is being used to do stuff that the inorganic world does not do. So the theme, life is defiance. And here I give you 7 examples of defiance. And when I use those words for today, I'm using them a little bit loosely. So this is meant to be a motivational or aspirational or inspirational introduction to life as defiance. But so I give you 7 examples, all of which defy the injunction of the second law to go to the terminally privileged state of a system, which is the state of maximum entropy. So, in the upper left, I point out that potassium ions, I don't know why they're little squares, that needs to change, but why that potassium ions are maintained in a gradient. And if you like, what happens actually is the potassium is pumped up its gradient. I'm going to come back to that in a little bit. Performing high fidelity polymerization. So this is a great example that we're going to have a lot of fun talking about, which is if we do the estimate based on equilibrium thinking, we will find that the fidelity of processes such as translation would be much more error prone than it's actually measured to be. And so that's interesting, in order to achieve that, something has to be done. Then the next one in the upper right, adapt to environmental change. This is subtle, and it's one of those things that we don't maybe think about, but my point here is that there are lots of examples both in inorganic science and in organic science, but let's talk inorganic first, where you have a dose response curve. So you have some sort of a response. As I increase the magnetic field, the magnetization of the material changes, or as I change the temperature, then some correlation function changes or something like that. So I have a dose response curve. But the thing about living organisms is that for a lot of their dose response curves, they can be shifted. In other words, if the system finds that it's not tuned correctly, then through the consumption of energy, it will actually change the dose response curve by moving it. So that's very, very important. Next is socks before shoes kinetics. So here's my foot, and here's a sock. And, I don't have a shoe, but when I get up in the morning, I take my sock and I put it on my foot, and then after that I add the shoe. And the point is that to draw one-way arrows, which is the way Jeremy Goodenow-Ardena puts it, is the original thermodynamic sin of biology. To make these one-way arrows, it really violates thermodynamics. But biological systems do break what's called detail balance, which I will talk about. And the way they do that is, once again, by paying energy. The lower middle build self-organized dissipative structures. There's tons of examples of that. And then I'm showing post-translational modifications and that kind of thing. And then the obvious one of just defying diffusion. So each one of these is a version of defiance. And I'm going to try to make that sort of more concrete as we go on. So what I wanted to do in this introductory vignette is to just sort of set the stage for this part on defiance, and then the one after that, the next section after that, which is in a certain sense about active matter. And I want to just remind us to not get too high on our horses. And what I mean by that is I feel confident, that in 100 years and even in 50 years, that people will look upon our understanding of the life phenomenon as being incredibly naive, despite the sophistication of the things that we can do now. And I just wanted to show you here that the nature of life and how we think about it has continually delivered up surprises. Now, I learned about some of these from a really wonderful new book that's coming out from Carl Zimmer, which I recommend you be on the lookout for. So this is early 2021 when I'm doing these vignettes. And Carl just wrote this really nice book in which he attacks the question of how is it that over the last, let's only focus primarily on the last 300 years, how have we dealt with this question? And so, on the upper left, you see from 1774, the discovery of Bonaventura Corti, who discovered what's now called cytoplasmic streaming, but looks like a perpetual motion machine. You look in a microscope and you look at the transport inside of a cell, and you see it's one directional, like a highway. And you say to yourself, well, I know that stuff like that has to cost energy, but it just keeps going and going and going. And so, that was the kind of thing that gave rise to vitalism, which I'm going to talk a little bit more about. Then, the CRISPR of its time was this work from Tremblay, where this says that this is a memoir that serves as a history of basically Hydra. And the reason I call it the CRISPR of his time is he couldn't keep up with all the requests to his lab to send Hydra. I think he was in Switzerland, if I remember correctly. And so what was discovered there was regeneration. You slice and dice this thing and it grows back and becomes a Hydra again. And then in the upper right, this is Galvani and Volta and their little battle about the nature of animal electricity. On the lower right, this is a paper from Thomas Henry Huxley, who was Darwin's bulldog. And maybe many of you don't know about it, but the original Challenger was not the space shuttle, but it was actually in the 1870s a voyage around the world by this ship that basically discovered the two greatest geological features on the Earth, if I remember correctly. It discovered both the mid-Atlantic ridge and the deep trenches in the Pacific Ocean. And what they did is they went around and they made measurements, to the point of tedium, but they discovered all sorts of interesting things. They found some goop on the bottom of the ocean, and Huxley thought that maybe they had gotten to the bottom of the origins of life question. And then on the lower left, I also just wanted to point out this issue of regeneration, which, this is a recent PNAS paper in which they take a 30,000-year-old tissue that's frozen and basically show that they can get fertile plants out of it. Again, why did I show you this? Because I wanted to make it clear that the nature of life is confusing, and it's confusing now. It's not confusing then, it's confusing now, even though it's easy to try and convince ourselves that, we're hot stuff and we figured it all out. So, so I already mentioned this about Corti, and I don't think I'll pursue it any further. I mentioned this, the vitalism debate on muscle action, so this goes back to Galvani and company. I already talked about diffusion, and I simply want to say that, if you look at Robert Brown's paper on the left, a brief account of microscopical observations made in the months of June, July, and August 1827 on the particles contained in the pollen of plants and on the general existence of active molecules in organic and inorganic bodies by Robert Brown. So, that's cool. Once again, trying to confront this idea of perpetual motion, the seeming, I'm not saying there is perpetual motion, I'm just saying the apparent perpetual motion offered up by living organisms. And here there was the nuance is beginning to emerge, because what Brown realized in looking at things like sphinx dust is, it's not unique to living organisms, and so there must be some energy lurking in this room that I'm sitting in. And I already mentioned, as I learned from Chris Darzinski, you take a liter of air and there's enough kinetic energy in the molecules there. Work it out for yourselves. I did. I mean, I didn't trust Chris when he said that. I mean, I trusted it that he probably had it right, but I needed to see for myself. So just add up all the 1/2 mv squares using the ideal gas law. You can figure out how many molecules that is. See how much kinetic energy it is. Yeah, you'll be able to lift a bowling ball up to the height of the ceiling. Then there is this really interesting debate that I've also mentioned already, between the Pasteurs and between Pasteur and the Buchners. And so look on the left. Alcoholic fermentation is a process correlated with the life and organization of yeast cells, not with the death or putrefaction of the cells, nor is it a phenomenon of contact, for in that case the transformation of the sugar would occur in the presence of the ferment without giving anything to it or taking anything from it. So his point was fermentation and enzyme action was the nature of life. And then the Buchners, well, in their case, through the discovery of Buchner, biology was relieved of another fragment of mysticism. The splitting up of sugar into CO2 and alcohol is no more the effect of a vital principle than the splitting up of cane sugar by invertase. So, as I said in my previous thing on Turing, that had to do with the dichotomy between positional information and Turing. I said, well, maybe we shouldn't be so worked up about the differences between those. Here, I would claim that both the Buchners and Pasteur were right. It was all good. So this is just to say that the nature of the life phenomenon is fascinating. And obviously, if I'm going to try and attempt, not poorly, very disappointed with this online nonsense of trying to give these vignettes, but it's what we've got. I'm certainly not going to run a class in my building at Caltech anytime in the immediate future. So here we are. So I tried to indicate that there's this puzzle about living phenomena, and now I want to take a little bit of an apparent detour in order to continue to make my point about the confusion that surrounds the life phenomenon. So in 2005, it was the 100th anniversary of the big year of Einstein, which you can see on the right. Those are 3 of his 4 big papers. So the top one is about what I just was speaking about, where he wrote down his beautiful derivation of the diffusion equation and worked out its properties and so on. And then the middle one is where we could say that he figured out the photoelectric effect, but he was frying much bigger fish, as usual with him, and came up with the photon notion of light. And then the bottom one, that's on the electrodynamics of moving bodies, and that's his paper on special relativity. So we had the 100th anniversary of that year, and many people opined about what had been accomplished over the last 100 years and what we might want to accomplish in the next 100 years, and what are the big questions of the day. And David Merman at Cornell was asked to speak on this, but the question that was asked was, if I talked about questions I would ask physicists 200 years after Einstein's Annus Mirabilis, if I could be magically transported to the year 2105. And so what's great about this article is that in characteristic Merman fashion, he cuts through all the bull and he gets right to the heart of the matter. And what he says is that most people's attempt to ask questions that they'd want to know 100 years hence were way too provincial. And so he tried to be imaginative and high level. And just to give you an example, one of his really nice questions was, what kind of device will you be using in 2105 that will look as weird to me as the laptop that I'm talking to you on right now would look to Einstein? I think that's a great question. And so why am I bringing this up? Because I wanted to tell you my candidate. I really believe that, and it's very simply stated, and it's a 200-year-old mission, which this is subjective. There could be people, very famous, well-known people that are way better at physics and math and science than I am, who would think that I'm foolish or naive or whatever, and that's cool. We each get to be judge in our own court. I'm judge in my court, and in my court, I feel very strongly about this one, and I have for 40 years. So, I doubt I'm going to change my mind about it anytime soon. And it has to do with the if you'll let me use harsh language, it has to do with the failure of thermodynamics to be what its name says. It's thermostatics, really. So I want to comment on that. So, we're living in this pandemic, and I can't help but think of Sadi Carnot, who's shown there in that picture. I think he died at age 37 of cholera. Something that I like to think about. I like to think about cholera, just because, here we are. The world is deprived of this great mind at such a young age, as a result of an infectious disease. And sorry, I'm going to editorialize for a second. The great Edmund Halley, who was the one who paid for the printing of the Principia, and did interesting things about the return. Obviously, about the comet, but he worked and interacted with Newton in a way that most people couldn't. But he also made the first actuarial table, I think, or one of them, and he did it for a city called Breslau. Oddly, I don't really understand that part of it, but I've looked at the data many times, and what he found is that half the population was dead by the age of 20. And so here's the editorialization, which probably is, maybe I shouldn't be doing, but when I listen to the foolishness of people who are protesting at Los Angeles Dodgers Stadium against vaccines, and the kind of stuff that I've heard in the last year about the pandemic, it just makes me sort of shake my head at the idea of, would these people, they don't acknowledge polio, they don't acknowledge the literally hundreds of millions of people that died from smallpox, they don't know about Ignaz Semmelweis, the Hungarian doctor who was vilified for trying to stop women from dying in childbirth by asking doctors to wash their hands. Would these fools, I'm going to call them fools, I'm going to go there, would these fools want their kid operated on by doctors not wearing gloves and not wearing masks? Really? I mean, seriously? Are they that stupid? I mean, okay, I guess I should stop. So anyway, it's just every time I see Carnot, I think, I would be dead for 23 years already if I had lived his life. It's sad. So Carnot was in the early days of thermodynamics, and one of the things I want to say that'll be one of the main messages of this course is that we can use physics as our model, in the sense that in the year 1800 there was no electric field. That was the brainchild of Michael Faraday. There was no entropy. That was in some sense the brainchild of Clausius, shown here. There was no Carnot cycle. There were many concepts missing. I'm not talking about factual knowledge. I'm talking about conceptual knowledge. And I already made this point when I went off about surprise earlier in the term. So Carnot, he knew about these various engine designs. They're Baroque, they're archaic, there are all sorts of weird gadgets on them. The best part of this one is you see this governor right here, right above the flywheel, which is basically a feedback system. And what he said is, that's all fine, but we can abstract all of the complexity of that diagram, or the middle diagram, or the bottom diagram, and talk about a simple concept of a cycle and two reservoirs at different temperatures, and we can say concrete things about the maximum work that we can extract from the system. So that's a great start to thermodynamics. And then people like Clausius, he, in addition to his macroscopic notion of entropy, which is great, and we'll talk about a little, he also was interested in kinetic theory and trying to answer the question of, can we continue to build on this great success of the mechanical worldview and use it to explicate what temperature and heat actually are? So bravo, this is really great stuff. I would say, for my money, that this whole subject came to its crowning achievement in this paper by Josiah Willard Gibbs in the Transactions in the Connecticut Academy of Sciences. It's a long article called On the Equilibrium of Heterogeneous Substances. And on the right-hand page, I show you this amazing thing, which, kind of takes the quotes from Clausius in the upper left and mathematicizes them. And if you want, the thing that's bugged me since I was 18 years old was the Clausius quotes up there. I didn't like the fact that they were words. I don't like the words version of the second law of thermodynamics. So, it says the energy of the world is constant and the entropy of the world tends towards a maximum. So Gibbs basically showed us how to use this entropy maximization as a variational statement about the terminal privileged states of systems. And then he had these clever ideas about, well, if it's not convenient to use the entropy maximization, then maybe you'll want to use an ancillary quantity, which is, for example, the free energy, and minimize that. And that's a beautiful simplification. So, this kind of thinking tells us what will happen if we have an isolated little world. I'm showing you 3 examples of my isolated little world. That external box is rigid, the external box, rigid, adiabatic, and impermeable. What that means is that I'm not allowed to communicate with it by pushing on it and doing work. I'm not allowed to communicate with it by using my flamethrower. I'm not allowed to communicate with it by blowing molecules on it. It's isolated. And then his point was, if you remove an internal constraint, the system will change. And it will change in such a way that it maximizes the entropy. So what I'm showing you here is the entropy of the left-hand side of the moving partition, the right-hand side of the moving partition. So the right side is in red, the left side is in blue, and the total entropy is shown in green. And what you're supposed to see is that there's a competition. If we slide the partition, we will increase the entropy of one side, but we'll decrease the entropy of the other. And so there's some optimal position at which to place that partition in order to maximize the total entropy of the system. And that's what we know as equality of pressure. So what I'm telling you is that the intuitive condition that we kind of carry around with us of mechanical equilibrium of a gas, for example, is the result of maximizing the entropy. And that pressure condition is really reflecting, if you like, the entropy maximization. The next one has to do with balancing particles. So if I put a little hole in the partition, what will happen is molecules will traverse that hole until the chemical potential on the 2 sides is equalized. And I have to say, it's a bit of a pity that we don't have a notion of chemical potential in our common vernacular. I could come to you in the morning and say, hey, what's the temperature like today? And that's the rate of change of entropy with respect to energy. That's wild. That's a really, but yet we have a name for that, which is temperature. And I could come to you and say, oh, when you were in the plane, did your ears hurt? Was there big pressure change? And that feels okay. But I can't come to you and say, hey, how's the chemical potential this morning? And that's a pity, because in a way, the chemical potential, to me, Gibbs is the crowning glory of classical thermodynamics, and the crowning glory of Gibbs is chemical potential. It's not temperature and pressure. It's really this beautiful idea that takes us back to the Turing things that I just talked about. Anyway, so that's the terminal privileged states. Now, what do we do about a system that's not there yet? Let's say it's not in its terminal privileged state. So it's going to move towards the maximum in entropy. Well, how do we think about that? Well, we've already given an offering on that in the form of diffusion, where we wrote down Fick's law. Fick's law told us how to relate the flux of mass across the interface that you see up here in part B to the gradient in concentration. And what I'm trying to show you is that this category of laws with quotes, they're phenomenological laws, and I'm going to give a vignette about phenomenology, and we wear it as a badge of honor. We don't apologize for it, or I don't. I'm happy about phenomenology. So at any rate, there's a whole host of them where we have flux is linearly related to degree of disequilibrium. So for example, Fourier's law, the degree of disequilibrium is given by the gradient in the temperature. And there's a flux of energy in the form of heat. Newton's law of viscosity tells us about the flux of momentum. That's really cool, super subtle. And what we're saying is that there's a transport of momentum because of the diffusion of momentum. So at any rate, there's, we have these kinds of principles, and they're helpful. I want to try to dig a little bit more into this notion of systems that are out of equilibrium and irreversible. And I think I will do it by reciting to you the biography of a famous and unfortunate egg. Humpty Dumpty sat on a wall. Humpty Dumpty took a great fall. All the king's horses and all the king's men couldn't put Humpty together again. That's it. It's a sad biography. So here's the point. If I were to show you the movie of this running backwards, you'd cry foul. you would say, well, that's not the way the world works. The world is irreversible. It goes in a particular direction. And Maxwell had something to say about this in the middle of the 19th century in a letter to his very good friend Peter Guthrie Tait. It was kind of a triumvirate of Tait and Kelvin and Maxwell, and they wrote letters to each other. And I like to think of them as friends, but probably competitors also, in some sense. So in this letter, he says, if we conceive of a being whose faculties are so sharpened that he can follow every molecule in its course, such a being whose attributes are as essentially finite as our own will be able to do what is impossible to us. For we have seen that molecules in a vessel full of air at uniform temperature are moving with velocities by no means uniform. That's a huge discovery. That was Maxwell's discovery, which we now know as the Maxwell distribution of velocities of gases. He's saying that there's a distribution of velocities, and some of the molecules are moving fast, and some of them are moving slow. So let's keep going. Though the mean velocity of any great number of them arbitrarily selected is almost exactly uniform. Now let us suppose that such a vessel is divided into two portions, A and B, by a division in which there is a small hole, and that a being who can see the individual molecules opens and closes this hole so as to allow only the swifter molecules to pass from A to B and only the slower molecules to pass from B to A. He will thus, without expenditure of work, raise the temperature of B and lower that of A in contradiction to the second law of thermodynamics. And the thing is, once we have that situation, we can lift weights. And for me, this section on defiance, I'm going to try and cast it as often as I can in the language of, well, can you use it to lift a weight? If the answer is yes, then there's things to be harvested. So here I give you 4 examples of demonic biology, where if you look at a biological system and you played the tape backwards, if you played the tape, you'd think to yourself, well, you're running that backwards. Like, let's take the lower left. I have a motor that packs a DNA into a virus, but if you release the motor, the DNA is going to come out. So when you show a movie of it going in, it looks like it's going the wrong direction. And of course, there's energy being expended to the tune of 1 ATP per base pair. The fidelity of translation shown in the upper left, that's a high, 1 out of 10 to the 4th amino acids is incorrect. And that is higher fidelity than you get from equilibrium alone. So, all of these are examples of that sort of thing. So this is just kind of to make this notion of the Maxwell demon clear, where if I show you on the left, if I open the trapdoor on the system where there's this inhomogeneity, what will happen is that over time it will bleed off. So in the middle, I show you this thing running it backwards. But in the third example, I show you a legitimate example where, in this case, I'm showing you the Maxwell demon doing, but in fact, there's pumps. There's biological pumps that do exactly what you would see in the movie on the right, which is that takes stuff from lower concentration and pushes it to higher concentration at seeming odds with the second law of thermodynamics. So I think I won't comment on that anymore, that one either. So just to finish up, what I've tried to do is to set the stage for the coming maybe 10 days, the coming number of vignettes. And I'm going to really try hard to tell you things that you won't find in books and that are kind of on our minds at the moment as we're trying to work through developing this theme of life as defiance as, I don't know if I could call it a principle, but as a motif, as an organizing principle. I'm always curious about, I used to like to talk about, if you held up the beautiful book by Bruce Alberts and company, Molecular Biology of the Cell, and you held up Physical Biology of the Cell, the things that are close to each other in our book are very different from the things that are close to each other in their book. And neither of them are wrong or right. They're just showing you that depending on how you look at the thing through the fly's eye, you come up with a different perspective on what is the thing that you would want to tell somebody else. And so here, what I want to do is I want to turn all of these different phenomena into the same thing, if you'll let me use the word same in sort of a physicsy way as opposed to a biological way. So that's the essence of what I wanted to introduce this evening, and I look forward to pursuing this theme in coming